In this lecture, I am going to look at some examples related to velocity analysis. The first example is of that bin which we have looked before. We have discussed the displacement analysis of this bin. Here we are to determine the angular velocity of the links and the dumper bin when the actuator throw O1A, this is O1A, this is given as 5 meter, and expansion rate is 1 meter per second. So, this actuator is expanding at 1 meter per second. So, throw is 5 meter and it is expanding at 1 meter per second. You have to find out the angular velocity of the links and the dumper bin. We have defined these vectors before during displacement analysis. Let us just go through them again. L1 is O1 O2. So, this is the L1 vector. L2 vector is O1 B. L3 vector is BA, which is the coupler, which is actually the bin. O2A is L4 and O1A is L. O1A is this vector. So, this vector is the vector L. From our previous discussions on displacement analysis, for this given actuator throw, we had found all these angles. Now, theta, the angle theta is this angle, that angle is theta, that was 49.45 degree, and theta 2, theta 3, theta 4 were all determined. Theta 3 is the bin angle. So, these were determined from the displacement analysis. Now, from the chain O1 O2A, which is this chain, we can write using the kinematics L cosine theta plus L1 is equal to L1 plus L4 cosine theta 4. We are using the coordinate system x y, the same that was used for displacement analysis. Now, if you differentiate this equation with respect to time, here you note that L and theta 4, these are functions of time. So, if you differentiate this with respect to time, you obtain this relation which involves L dot, theta dot and theta 4 dot. Of this we only know L dot. Next, if you look at again these two expressions, these two equations, and divide one by the other, you can find out tangent of the angle theta, which turns out to be this ratio, and if you differentiate this with respect to time, you have this expression relating now theta dot and theta 4 dot in terms of the angles theta and theta 4. Since theta, theta 4 are known to us, therefore, we can find out we have this relation between theta dot and theta 4 dot. Now, let us look at the previous expression that we had determined. So, these are the two expressions. This involved theta L dot, theta dot and theta 4 dot, and here I have relation between theta dot and theta 4 dot. Therefore, if I eliminate theta dot between the two, then I have a relation between theta 4 dot and L dot. So, if you eliminate theta dot and simplify, then you have a relation between L dot and theta 4 dot. Now, out of this, L dot is given to us, the expansion rate is given to us, and from the displacement analysis we already have theta 4 and theta. Therefore, we can determine theta 4 dot, that turns out to be minus 0.658 radians per second for given expansion rate of the actuator as 1 meter per second. Now, once we have theta 4 dot, now we can use the relation between theta 4 dot and theta 2 dot and find out theta 2 dot. This was our relation which we have found from the analysis of this 4R chain. The 4R chain is O1 B A O2. This is the 4 bar chain whose analysis we have done previously, and we have found this relation between theta 2 dot and theta 4 dot. Now, using that, since we know theta 4 dot now, we can find out theta 2 dot, which has been determined here. So, from the displacement analysis we know these angles, from the previous velocity analysis we know theta 4 dot. So, therefore, from the above expression we can now find out theta 2 dot. Finally, we need to find out the angular speed of the bin, the rotation of the bin. Now, this expression we had derived during displacement analysis of the 4R chain. So, tangent of this angle theta 3 is given by this ratio, which is in terms of theta 2 and theta 4. If you differentiate this with respect to time, you get a complicated expression which is doable, but it is a little lengthy. In that, you involve theta 3 dot, which we want to find out, theta 2 dot and theta 4 dot, and the joint angles theta 2 and theta 4. We have already found out theta 2 dot and theta 4 dot. Therefore, by just substituting these expressions and the joint angles which we already know, we find out theta 3 dot. So, that completes this problem in which we had to find out the angular speeds of all the links, including the bin, and this theta 3 dot is actually the angular speed of the bin. A negative sign indicates that it is decreasing, therefore, it is in the clockwise direction, the rotation is in the clockwise direction. In the next example, we are going to look at this car lift mechanism. In this mechanism, it is given that this length L is equal to 2 times this length B, and this length is 2 meter. So, the problem says the hydraulic actuator expands at a constant rate of 1 meter per second. Determine the upward speed of the platform when theta equal to 30 degree. So, this is the angle theta, which is specified 30 degree. So, at theta equal to 30 degree, what is the upward velocity of the platform? we define these vectors in the coordinate system x y with origin at A. So, this vector is the L vector, AC is this vector B, and this vector is vector S. Therefore, from the vector loop equation we can write B as vector L plus vector S. Now, if you look at the components, of the vector B, L and S, from the x component we have the first equation, and from the y we have the second equation. Here we involve this angle theta s. So, this angle is theta s. Okay, so, these are our relations. If you eliminate theta s, then in order to eliminate theta s we take L on this side, square and add, and we have this expression of s in terms of theta. So, this is our relation of s with theta. If you differentiate this with respect to time and simplify, we involve s dot and theta dot. L and B are constants, therefore, this involves s dot and theta dot, and it also involves s, which we already know. Now, here we have another displacement which actually gives us the motion of the platform, which is h. So, h can be related in terms of this length AD and the angle theta, and is given by 2b sin theta, and if you differentiate this, this is going to relate h dot and theta dot. Now, we have two relations, one is involving s dot and theta dot, the other relation involves h dot and theta dot. So, if you eliminate theta dot and use the relation of s and theta, then you come up with this expression. Now, here we have s dot related to h dot in terms of theta. Now, from the displacement analysis we have already found out theta. So, we are given this theta as 30 degree. So, at theta equal to 30 degree we are given s dot as 1 meter per second, other data, the link length data are all given. Therefore, we can find out h dot, which turns out to be 2.146 meter per second. Next, we look at the Nuremberg mechanism, which we have discussed before in the context of displacement analysis. Here it is given that the pin A slides to the right at 1 meter per second. In other words, S dot is given as 1 meter per second. We have to find out H dot, basically the speed of the vertical travel speed of the platform. Now, we have looked at the displacement analysis of this mechanism before and we had related S and H in terms of theta, which are shown here. Now, once again, if you differentiate these two expressions, you involve S dot and theta dot and H dot and theta dot. If you eliminate theta dot, you relate H dot and S dot. Now, when S dot and theta are given, so here it is given as 1 meter per second and theta is given as 30 degree, you just substitute, you will get the expression of H dot. So, that completes this example. So, with that I will close this lecture.